Okay, we're looking at practice problems from kinematics, which start in our notes with these guys up here. And so we have 1 through 5. 1 through 5 will be the first kinematic ones, and then 6 and 7 will be the two free fall problems in the free fall section. And then I think there are a couple others that I'll call 8 and 9. We'll just tag them in the description so you can jump to that timestamp. Anyway, all right, we had derived kinematic equations that are these guys: v final, v equals v initial plus acceleration times time. That was from our slope. Delta x, displacement, is 1/2 v initial plus v final times time. That came from the area under the curve for the velocity time graph. And then we've got these other guys that we also derived. There's delta x, and this one, our last one, is v final squared equals v initial squared plus 2a delta x. So in any of our problems, these first few are much more straightforward. They just give you values, have some pictures, and you just select what do I know and what equation is relevant for finding what I don't know. So we have to list out what we know. So I'm going to do all my work below here. I'm going to put all my work. So a speedboat pictured right accelerates at 2 meters per second squared. Okay, I know that. A is positive 2.0 meters per second squared. Write it out. From 6 meters per second to some unknown final velocity. So that's pretty clear that my 6 meters per second is the initial velocity. And make sure you check the units. The units tell you what the quantities are. You need to know what the symbols represent. You need to know what units each quantity is expressed in. Those things you need to memorize, otherwise you have no idea what these symbols represent. Final velocity is unknown. That's what we're looking for. Our time is 8 seconds. Determine VF, and also the boat's change in position. So that's my delta x equals question mark. So I can solve one at a time. Let's start with delta x this time. If I'm looking to solve for displacement delta x, I know I have acceleration, initial velocity, I have time, delta x, and that points me to this equation as being relevant because it has delta x, it has the thing I want to find, it has vi, it has t, it has, I'm sorry, I wrote g in there because we're so used to doing free fall recently. All right, it has A, the acceleration was given for this ship, boat, 2 meters per second squared. So we got all this stuff, so that's the one we want to use. All right, so first, show which equation you're using so you're not getting tripped up. All right, that's the stuff. What am I solving for? Delta x, so it's already isolated on one side of the equal sign by itself, so I don't need to rearrange it. So I can substitute initial velocity is 6 meters per second, time is 8 seconds, plus 1/2 acceleration is 2 meters per second squared, time is 8 seconds. So I have 6 times 8 is 48, that's meters per second times seconds is meters, plus half of 2 is 1, times 8, sorry I need my t squared. So I have half of 2 is 1, 8 squared is 64, so I have 64. And I have second squared cancels out with second squared, so I'm again left with meters, which is good. And 48 plus 64 is 112. I'm pretty sure we did that one together in class. Alrighty, okay. And then that's one value. Once you find it, you can go ahead and put it in here in our list of stuff that we know, and then it can be useful to then help you find your last thing you're looking for. So VF, I have VI, A, and T. I might as well just go with this guy. That's supposed to be a V there. VF equals VI plus AT. Final is what we're looking for. It's already isolated by itself, so we don't have to rearrange the equation. 6 meters per second plus 2 meters per second squared times time, 8 seconds. 6 plus 16 is 22 meters per second. Boom. Okay. Now we're doing graphs. So I'll call this position versus time, velocity versus time, acceleration versus time. And I'm going to call to the right is the positive direction. That was already given in the picture. But it starts off with a positive velocity. It increases its speed because it has an acceleration in the same direction, and it has a final velocity that's greater. It's good to check that. 22 is greater than the initial velocity of 6. That makes sense. It has a positive displacement. That makes sense. It's moving in the positive direction. So since it's speeding up, I should have a position time graph that indicates speeding up, but it shouldn't start with the 0 slope because it's already moving at 6 meters per second. So I should start it at some non-zero slope. That's my attempt at a quadratic function there. This time is 8 seconds. My final position at 8 seconds is, if this is 0 where it's starting, then 112 is where it ends. And I'm going to make sure every time we do a graph, you got your units there on each axis. Time, meters per second squared. Okay. And usually we'll call, I'm going to change my position time graph to be x. Position x is a function of t because that's the variable we're using. Velocity starts at 6, right? And increases linearly until it gets to 22. And that's at, you don't have to draw the dotted lines in when we do a graphing question on a test. This is a horrible line. Let's do a better job. And that's linear. And then the acceleration we know is a constant, positive 2 meters per second squared. And I can say that's 8 seconds right there. I don't need my units. I already got my units on the axis. Okay. Second one. We have aircraft carrier accelerates a jet from rest, so I know initial velocity is 0 to 62 meters per second. With an acceleration of 31 meters per second squared. Determine the distance across the deck. Well, it's going to be a displacement. How far it traveled. So delta x equals question mark. What else do I not know? Time t question mark. All right, so we take a look. We got VI, we got VF, we got A, and we want to find t or delta x. Really, I just care about delta x. That's all the question's asking for. So if I want an equation that has VI, VF, A, and delta x, I believe that's my fourth one up here. All right, there's VF, VI, A, delta x. So let's do that one because then we have to rearrange to solve for a delta x. And that can be good to look at. So V final squared equals V initial squared plus twice A delta x. What do we want to find? Delta x. So here's my step-by-step algebra. Subtract VI squared from both sides. I want delta x, so I got to divide both sides by twice A. VF squared minus VI squared over 2A equals delta x. And then I can simplify because I know initial velocity is 0. It starts from rest, speeds up across the deck, and hopefully takes off. So VI is 0, so this is just VF squared over twice the acceleration. It's delta x. All right, we have a working equation. Now we'll substitute. What is VF? 62. So this is 62 meters per second. It's velocity, yep, so meters per second, and that's squared over twice the acceleration. So that's 2 times 31. All right, there's my acceleration, 31 meters per second squared. So twice that is 62 meters per second squared equals delta x. Well, 62 squared over 62 is 62. And my units get adjusted. I got meters squared over seconds squared divided by meters over seconds squared. I'm only left with meters up top. So 62 meters is our displacement for this guy. Remember, we can always check stuff by using other equations. So let's say we got 62 meters and I don't know, I'm not entirely confident because I did it quickly and I want to check because I got some extra time. So maybe I solve for, pretend like I'm solving for time first and I haven't found delta x yet. Okay, well I got VI, VF, A, so I can solve for t with the first equation. VF equals VI plus AT. Final velocity 62, VI, AT. Let me solve for A. Or I'm sorry, solve for t. All right, final velocity is 62. Initial is 0. So divided by an acceleration of 31 meters per second squared is time. So 2 seconds. That's how much time it took. So now let's find delta x again, but we'll use a different equation. Let's say we could do VIT and 1/2 AT squared. Let's try that one. See if we get 62 again. Delta x. So I'm checking my work now. If you're like, why are you doing this again? VIT is initial velocity 0, right? So this is just this. Acceleration's 31 meters per second squared. T is 2 seconds squared. So I have 2 squared is 4. So I have 4 seconds squared, but times 1/2. Right? Do I need to write all that out? I guess I will. Okay. 1/2, 31 meters per second squared. 4. Remember, our 2 gives me squared seconds. Half of 4 is 2. So I have 2 seconds squared times 31 meters per second squared. Second squared goes away, and we get 62 meters. Yay! Okay, so check my work. 62 meters is the answer. Let's do graphs. So here's position x versus t, velocity versus t. Every time I got to make sure I have my units. Meters per second, seconds, and I got acceleration. Meters per second squared, time, seconds. All right, so we have jet. Initial velocity is 0. We'll do velocity first, up to 62 meters per second. So there's 62, right there. We know it takes 2 seconds. Very good. Okay. Acceleration was also given, right? 31. We're calling to the right to positive direction, so there's 31. It's constant. Our accelerations are always constant. We're not going to have crazy curvy or linear accelerations. That was a really straight line. All right, now we have position versus time. So the thing is speeding up. It's moving in the positive direction, and it goes from, let's say, a position of 0 to wherever it ends up. That's what we had to find first, which is the 62 meters. So up here it's final position. And we're speeding up from 0, so I got to do my best to indicate that it has 0 slope at the very beginning. And that's that's quadratic. That's at 2 seconds. Okay, so there are my graphs for number 2. Number 3. We're running out of space here, so let's do this real quick. Which one's the copy? That's copy. No, well. Uh-oh. Error. I don't know what just happened, but here we go. Number 3. All right, a spacecraft is accelerated by applying a reverse thrust rocket. So the thing is, the spacecraft slows. It's slowing down with a constant acceleration with a magnitude of 10 meters per second squared. So notice it just gives you an amount, not a direction. But you have to remember, if we're slowing down, velocity is to the right in this picture. Notice our directions down there, so it's positive. If we're slowing down, velocity and acceleration are in opposite directions. So acceleration points this way. So that acceleration is going to be a negative 10 meters per second squared. Spacecraft initial velocity is 3250 meters per second. It's slowed over a distance of this amount. What's its final velocity? So VF is question mark. VI we know is 3250 meters per second. Over a distance tells me the displacement, which is 215 kilometers. And what else? Acceleration is, I'm going to put in my minus there because I know it's pointing in the opposite direction of the velocity. And we don't know time. Okay. All right. Firstly, delta x is expressed in kilometers and everything else is in meters, so I'd probably just change delta x rather than change everything else to kilometers per second and kilometers per second squared. So, I mean, that's up to you. 1, 2, 3. That's going to be meters. All right, or we could express that in scientific notation and give us less writing. Whatever. Let's look at, we want to find V final. So I know that I have my fourth kinematic equation could be useful here because it's the one with no time. So if I'm looking for VF and I also don't know T, this is the one to go to. We're looking for VF, so I'm going to isolate it by itself. And I have VI squared, so this is, just to be super clear, that's squared plus twice, and then here comes the acceleration. It's got to be negative times delta x, which is now 215,000 meters. All right, I really hate to write all of this out. I must move my parenthesis there. Rather than just, I mean, I would just put this all in the calculator at once and be careful with my parentheses, but I'm going to do each thing, even though we're going to get some big numbers here. So this first value, 3250 squared, is 105 million. Oh, yuck. Yeah, it's, or no, is that 10 million? Yeah. 562,500. So that's meters squared per second squared plus, or sorry, it'll be minus because I got my minus sign there. So minus 2 times 10 is 20. And then I've got my 215,000. Should have just used scientific notation. 4.3 million. Let's put some commas in there so you can actually see. And this is, because it's being multiplied, I got meters squared over seconds squared. 123, yep, meters squared per second squared. All right, so 10.5 million minus 4.3 million, square root of that. No problem. All right, so what is 10562? 10562, I'm using my calculator right now. That's why I'm not writing anything. Minus 4.3. 1, 2, 3, 4, 5. All right, so 6,262. Yeah, so this is square root of 6,262,500 meters squared per second squared, and then VF equals the square root of that guy. I'm rounding now to 2,502. And the square root of meters squared is meters, and the square root of seconds squared is seconds, so we get our meters per second squared. Okay, so there's VF. We found it, 2502 meters per second. And we said it's slowing down. I mean, the question says the object's slowing down. So our initial velocity was positive 3250. Our final velocity is less than that, 2502. So it has slowed. That's good. And we needed to use our appropriate pluses and minuses indicating direction for the acceleration in order to make sure we get that. All right, seconds, meters, graphs now. Acceleration, meters per second squared, time, seconds. All right, acceleration, let's start with acceleration. Why not? It's minus 10. It's constant, all right? I already got my units up here, so just write the number down there. And then the time, I didn't figure it out, but like you can go practice, figure it out. What is the time for this? When we have all the other kinematic quantities, you can surely find time. And make sure you get a positive value for the time. If you don't get a negative value for the time, then you've messed up a plus or minus somewhere. All right, velocity. Let me think about it. Is it speeding up or slowing down? It's slowing down, right. So it's starting with the high. Is it traveling in the positive direction? Initial velocity, yeah, okay. So there's the initial velocity, 3250. It's slowing down. What does it slow down to? there's the V final. The arrow representing the V final was 2502, right? Yeah. All right, so 2502 is, you know, somewhere lower. All right, so it's slowing down over the course of however much time this takes at a constant rate of minus 10 meters per second squared. And so here this would be, I'm just going to draw in the dots so you can see what I'm talking about. This would be whatever the T final is. Initial T is 0. And we went from 3250 to 2502 meters per second. It's traveling in the positive direction the whole time. I'm just going to put a T final over there. Okay. Position. We'll say it starts at 0 position because we don't know where it starts. And it is moving in the positive direction. And it is slowing down. So I need a relatively steep slope to begin with at position 0 times 0. And then it needs to approach a less steep slope, but it shouldn't be a flat 0 slope at the end because that would mean it came to a stop. So, let's start at the origin, please. Like, there's pretty steep, and there's less steep. It's still a quadratic function, but I'm going from, to illustrate my slopes, because remember, on the position time graph, the slope is the velocity. So there's my initial velocity is represented by that slope. So the slope of that green line right there, let me just redraw this red line. It's so bad. Sorry, it's hard to... Okay, that'll do. And then the final velocity would be the slope right around here at this point. So there's V final. That's the 2502. Still positive, so it's still traveling in the positive direction, but it's less steep, meaning slower speed. Initial was 3250. Right? Okay, and then this time that lines up here is going to be T final. And the final position is 215, you know what, let's make this kilometers so I don't have to write the whole thing out. 215 kilometers away. Okay, graph's a little different for that one, but same exact application of our motion graphs from before. All right, number 4. Elevator is moving upwards with the velocity of 11 meters per second. Here's my velocity vector, the arrow. Okay, that's the initial. And then 3 seconds later, okay, so 3 seconds of time is elapsed. The elevator is still moving upwards. Okay, well, there's my elevator, still moving upwards. And its speed has been reduced to 5 meters per second. So now its velocity is, let's call it P final, after 3 seconds is 5 meters per second. They're still positive because it's still moving upwards. And so I am calling up the positive direction, which means down is the negative direction. Important to do this thing over here. Say what you're calling each direction and help prevent you from mixing up the pluses and minuses with little g. Okay, what is the average acceleration of the elevator during the 3-second interval of time? So we know, let's just make a nice, more organized list of what we know. VI, VF, T, A is what we don't know, and then time we also don't know. No, yeah, we do. I already wrote that. What else do we know? We don't know delta Y. All right, so that's the vertical displacement, how far it's traveled. So we have VI, VF, T, and we're looking for A. Well, here we go. Okay, what are we looking for? A. Solve this equation for A. VF minus VI divided by A equals time T. That's not what I'm looking for. Yeah, that is what I'm... No. Sorry, y'all. Sorry. End of the day. VF minus VI. Come on, Stacy. Equals AT. Always do it step by step if you start doing stupid stuff. And then I'm looking for what? A divided by T. VF minus VI over T. A. Okay, which is also just the definition of average acceleration. Now we can substitute. Final velocity was 5 meters per second. Initial velocity was 11 meters per second. Check my thing. Is that correct? V final, V initial, final minus initial. Yep. Time, 3 seconds is A. So 5 minus 11 is minus 6 meters per second over 3 seconds equals A. So 6 over 3 is 2. I keep my minus sign. Meters over seconds divided by seconds gets me the appropriate units, meters per second squared. All right, so A is a minus 2. So if I draw in my acceleration during this time of 3 seconds, the elevator experiences a downward acceleration. So my arrow indicates, my physical blue arrow I've drawn indicates the direction, and the amount is 2 meters per second squared. So down is negative, minus 2 meters per second squared. There it is. And that's when we have slowing down, is when the velocity is in one direction. There's the velocity initially. And my acceleration's in the opposite direction. That's when we have slowing down. And indeed, the elevator slows to 5 meters per second. All right, graphs. Let's call it y as a function of t, because that's, vertical axis. Meters per second, time, seconds, a, meters per second squared, time, seconds. We know it takes 3 seconds, so let me just mark that first. I know the acceleration is constant and it's minus 2, so there you go. That's supposed to be flat. Okay. Our velocity is going from what? Upward, so positive 11 to then down to 5. So there's 11, there's 5, and all the way at 3 seconds is where I said I'm going to draw that. So like that. Okay, and this guy should be right up there. So there's 11 meters per second down to 5 meters per second. So constant slope, it's negative. Remember, this is a constant slope. It's linear. It's a negative slope. So that tells me my acceleration is a constant negative value. And the velocity is always positive. The acceleration is a constant negative, so they're opposite directions. That means slowing down. Position, we're traveling in the positive direction the whole time, right? Because our velocity is positive the whole time. But we're slowing down. So since the slope on our position time, my y versus t graph, since the slope of that graph is the velocity, I need to start off with the slope of 11, so some relatively steep slope. And then it needs to indicate slowing down so it gets less steep or approaches 0, but it doesn't get to 0. It only gets to 5 meters per second. We'll say we start at the origin. I gotta stop. I'm going to draw this just so I know where to stop. So like there. And we're starting with a slope of 11 and going to, it's going to be hard for me to draw decently well, because I can't get to a 0 slope. Okay, so just like before, that'll work. Here's my initial velocity is positive 11 meters per second. That's indicated by the slope right there. Time equals 0. And then my final velocity is my slope right at 3 seconds, which notice I've made the slope not 0 because it's not 0. It's what? 5 meters per second. Both those slopes are positive. Both my velocities are positive at 0 and 3 seconds. Elevator's still moving up. Both those slopes on the position time are positive, and they represent the velocity. That's all I can say about that. Okay, 5. A race car has a speed of 80 meters per second when the driver releases the drag parachute. So VI is 80 meters per second. The parachute causes an acceleration of minus 4 meters per second squared. How far will the car travel before it stops? That means V final must be 0. Time, I don't know. How far is delta x? I don't know. But that is what I'm asked to find out. All right, so let's jump right into finding delta x. We could find t. Find t on your own so you know where it would be on the graphs when you make them. Or better yet, pause this, solve the problem, do the graphs, and then come back to it and play again. Delta x, let's solve that first. I know VI, A, VF, delta x. I don't know t, so I'm going to use an equation that doesn't have t. The car is slowing, which is why we have a negative acceleration. No, let's not say that. It's why we have an acceleration that's opposite in direction of the velocity. So the velocity is positive and the acceleration is negative. That indicates, because they're opposite directions, a slowing down. My velocity could be negative 80 meters per second, and my acceleration could be positive 4 meters per second squared. That wouldn't change anything. It would still be slowing down. It would just change which direction I'm calling plus and which I'm calling minus. Remember, that's arbitrary. That's up to you. But you have to be consistent once you choose. We're looking for delta x, so let's rearrange this equation step by step. Subtract vi squared from both sides, then divide by twice a, because we're looking for delta x. So there's vf squared minus vi squared over twice a equals delta x. And now we can substitute. Final velocity is 0, so I've got minus vi, what? Yeah, I'm sorry. Minus vi squared over twice a, because it's 0 minus vi squared, so I have negative vi squared. Twice the acceleration is downstairs, and there's delta x. Okay, we're isolated, simplified, because vf is 0. Now we'll substitute. So I have minus, what is vi? 80 meters per second squared. And then I've got over twice the acceleration, which is minus 4 meters per second squared. Delta x. That exponent, this vi squared, the exponent is squaring the initial velocity, and then that entire term is negative. Okay, because you're subtracting the square of vi from 0, which means you get a negative number when you subtract any number from 0, as long as that number isn't originally negative. And if you square it, of course, it's not going to be negative. So just bear in mind this minus sign stays there. Otherwise, you're going to get a plus or minus in your answer that won't make physical sense, which is why you should always go back and think about whether it makes physical sense. All right, so we have now minus a squared over twice the negative 4 acceleration. So I've got minus 6,400 meters squared over second squared over minus 8 meters per second squared. So that leaves us with just meters up top. Right? That's our units are going to be meters for our displacement. And then 6,400 over 8 is 800. Oh, that's a pretty long distance there. All right, now I'm breezing through it. So let me say, hey, let me check my work. I could go and find t first and then find delta x another way. So let me check that real quick. BF, or you pause and you do it. I'm going to find time and check my work. VF minus VI over A equals T. Final velocity is 0. Initial velocity is 80. So I got minus 80. Acceleration is minus 4T. So 80 over 4 is 20 seconds. That's a long time to slow down. Right? That's an S. 4 times 20 is 80. Yeah. All right, it's a positive value for the time, so I'm using my pluses and minuses properly because I should have a positive value for the time. And then we'll find delta x from a different guy here, VIT plus 1/2 AT squared. So delta x, what we're looking for, initial velocity is the 80, time is 20, plus 1/2 acceleration is the minus 4. Time is 20 squared. So 20 times 80 is, we have 1,600, right? And then these are meters plus 20 squared is 400, divided by 2 is 200, times 4 is 800, so that's 1600, and then that's negative, so it's minus 800. So 1600 minus 800 is 800 meters. All right, so that agrees with what I did over there. Cool. Graphs. So can we fit our graphs over here? Yeah. Here's position in meters, time in seconds, velocity in meters per second. Please always make sure you include the units. Got to. T in seconds. All right. Start with the acceleration, because that's easy. It's constant. So negative direction, 4. Constant. Negative acceleration. We found the time, didn't we? What is it? 20 seconds. So I can put a 20 right here for 20 seconds. All right, this is also going to be 20 seconds. Its velocity, what's this thing doing? It's traveling in the positive direction because it has 80 meters per second. In the positive direction, the acceleration's in the opposite direction. So it's traveling in the positive direction. It starts with a high velocity and it slows down to a velocity of 0. So this has to be 80 up here where we're starting. Down to, boom, velocity of 0 at 20 seconds. All right, notice my constant negative slope. This is -4 there, please. Okay, and then position, it's always moving in the positive direction. I get the positive 800 meters from my displacement indicates that it is a positive displacement. We aren't given an initial position, so call it 0. And what is it doing? Speeding up or slowing down? Slowing down. So my final slope of the position time graph should be a 0 slope to reflect the 0 velocity, which is right here on my velocity time graph. And it starts with the 80 meter per second velocity. So I need to be very steep and approach 0 at the 20 second mark. There's 20 seconds. Okay, so I'm doing my best to indicate that the slope here is 0. B final is 0. And then our initial velocity is this slope. That's our V initial is 80. Okay. All right, free fall problems. I still have my equations listed over here for free fall. One of the issues is making sure to use the appropriate pluses and minuses. So in this case, I'll solve it the way the problem indicates as far as the directions are concerned. So down is the negative direction. So a stone is dropped from rest. Okay, VI is 0. From the top of a building, it takes 3 seconds, okay, 3 second time, to reach the ground. What is the height of the building? Well, it's free fall. So I know acceleration is g. The magnitude, I use absolute value bars to remind you of that. The magnitude for problem solving we can use is 10 meters per second squared. I haven't said anything about the direction. I've just said the amount of the acceleration is 10. Now because the downward direction is the negative direction, look, it's right there. Since down is negative, I'm going to use a minus sign to indicate my acceleration is in the negative or downward direction. Okay, what else do we need? VF, we don't know. Delta Y, because we're vertical. Vertical displacement is unknown. And if we want to know the height, then we want to find out delta Y. So I need an equation that has the initial, time, acceleration, and delta Y. So the one that's missing VF, and I can come over here and see my quadratic function there is missing it. So let's copy that guy down. We'll do it right here. Delta Y, because we're vertical, is VIT. Now I put minus because down is negative. 1/2 g because my acceleration is little g, t squared. So initial velocity is 0, so this just becomes minus 1/2 gt squared. And I already solved for delta y, so minus 1/2. We round to 10 for our problem solving in test, but not in the lab. Time, what is time? 3 seconds squared. So delta y is minus 1/2 of 10 is 5, and then times 9. 3 squared is 9. So I got, whoa, minus 45, get out of here, meters. All right, so the ball, whatever this is, a stone is displaced vertically 45 meters in the downward direction. So the height is 45 meters, because you wouldn't express the height of a building as a negative. That doesn't make any sense. That's just a distance, a length, a scalar value. Our displacement tells us the magnitude and direction. We'll do graphs. Go ahead and find out what V final is for that. I mean, it's just GT. So here's position. We'll do Y. Y meters time seconds. Here's velocity in meters per second times seconds. Here's the acceleration graph. Free fall. So I called down the negative direction here. You can perfectly easily solve this problem by calling it down the positive direction. Remember, that part's arbitrary. But I've called down negative, so I need to indicate that I have little g, which is in the negative fourth quadrant, because I'm calling down negative, and little g always points down. Velocity. My velocity, it's released from rest, so it starts from 0. And my velocity is always pointing down. There's the velocity after one second. Here's the velocity after 2 seconds. Here's the velocity after 3 seconds. So it's always a negative velocity, and it's increasing. It's speeding up. And there's time. I forgot to put my time in. Okay. And then our final velocity, you go figure that out. I mean, it's 30, but position versus time is traveling in the negative direction. Let's say that the top of the building is the 0 position. So it's traveling in the negative direction. So we should be in the fourth quadrant, or we should be drawing our thing towards the fourth quadrant to indicate we're moving in the negative direction, and we're speeding up. So we're starting from rest, which means 0 slope, and we're speeding up. And there, that's fine. Let's call that right there 3 seconds. Right. And so I start off with a slope of 0, indicating my initial velocity is 0. We're traveling in the negative direction. And here's my steep negative final slope, which indicates my final velocity is whatever it is, about 30 meters per second. Right? It's GT. It equals VI plus GT. And it's negative. I should put that in there. Negative velocity. All right. Then let's also mention that it would be perfectly reasonable to say that the ground over here where it hits is the 0 line, and up here is its starting position. So there's Y initial and Y final is 0. You could do it like that, and your graph wouldn't change shape. You've just translated it upwards on the y-axis to say here's the starting position. I'm trying to draw the same graph here. And there's the ending position, so that this would be, what is it, 45? The distance here would be 45 down to 0. And if you started at 0, then this distance would have to be 0 down to minus 45. You draw it either way. It depends on what you call your 0 position. So either one would be acceptable on the test. Okay, last free fall one. Referee tosses a coin straight up with initial speed of 5 meters per second. In the absence of air resistance, how high does the coin go above its point of release? So how high does it go? The highest point has a velocity of 0 because it stops for an instant. Got to remember to infer that. And then, well, I mean, it's given in the picture, but what else? Acceleration we know is little g. I'm just going to say the magnitude I know is 10 meters per second squared. I'll decide on my pluses and minuses later. I will do what the picture says to use, which is to say call up positive, which means my g will be negative. And what else? Do I know time? No. Do I know the vertical displacement? No. Okay. So I'm asked to find how high it goes, so I need to use a kinematic equation that does not have t in it, and I know that's this one. And I'm using down negative, so minus 2g delta y. So whatever term that g appears in, the plus or minus that precedes this term with g in it, that's the plus or minus that you change depending on what you're calling the direction of downward, or the direction that little g points in. What are we looking at? Delta y, that's what we want. How high does it go above its point of release? So we solve for delta y. So vf squared minus vi squared equals minus 2g delta y. And then I need to divide by 2g. Minus 2g equals delta y. I've gotten delta y by itself. Now final velocity is 0. All right, so this is 0 because it stops for an instant at the top. That's a 0. So 0 minus initial velocity squared. So I can simplify this one more time and say minus vi squared over minus 2g equals delta y. And then I can say, oh, well, I can simplify that once more because it's minus something over minus something. So I have vi squared over 2g is delta y. Now we substitute. Initial velocity is at positive 5. So I have 5 meters per second squared over twice g is 2 times 10 meters per second squared is delta y. And so we got 25 meters squared per second squared over 20 meters per second squared is delta y. And then I've got 5/4 or 1.25. And what am I left with? Just meters up top. So I have a positive displacement of 1.25 meters. That's how high the coin goes if it's launched with an initial vertical velocity of 5 meters per second and it experiences no other forces besides gravity. That's what gets you allows you to use free fall acceleration. There's no other force besides gravity. So that's why we always say in the absence of air resistance. Graphs. This is going to be y versus t. V in meters per second versus t seconds. And A in meters per second squared times seconds. Okay, we call down negative. So little g is boom. Oh dear. Okay, and then what else? Time. What is the time? Did we not solve that? You figure out the time. T final. Okay, velocity. It starts with a large velocity. It's positive. Look, it's pointing upwards, and we called up positive. All right, so that's where it starts. That's going to be at 5 meters per second. That's a 5. And final velocity is 0 because we're just considering its motion from release up to its highest point where it slows down and stops for an instant. So there it is. And then we've got a positive velocity the whole time that slows down and reaches 0. There it is. All right. Now let's say we're starting at is a 0 position. It's traveling in the positive direction but slowing down. It starts with a high velocity of 5 meters per second, so I need a steepish positive slope that approaches 0 slope and then eventually gets to 0 slope at t final, which we'll draw right there. And we'll draw some dotted lines up here to help me draw it. Okay, so high velocity to start means it has a steepish slope. And that's not going to be curvy enough, I don't think. Oh, that's pretty good. There we go. Okay, so there's our initial slope, which is our initial velocity, which is the positive slope, and 5 meters per second. Slope is 5, and then we end with flat. V final is 0 because at the top of its flight, its velocity is 0. Okay. All right, so there's all of those with the graphs as well. And yeah, there you go. So we will look at a couple of these other problems. If we haven't reviewed the dynamite blast one in your class, we will be sure to review that, or you can just pause it and look at it, I suppose. There'll be a few other a little more complex, a little more thinking involved problems, kind of like this guy, that we'll look at on the first couple of days of class next week. I'd rather do a few more practice problems and then have our test maybe one day, pushed back one day from what's scheduled right now. But you'll know for sure on Monday or Tuesday whenever we meet first. I hope that's helpful for those of you who decide to watch it. People were asking for reviews of those problems. And that's it. Have a good rest of the weekend or whenever you're watching this. Adios.